My name is Scarlett Simmon, and I'm going to take you guys through Lab 2, which is motion of a falling object. So first of all, here are the things I'm going to talk about today. So the purpose of this lab is to throw an object, observe its trajectory, and depict how gravity and drag affect the movement of the object, and then to graphically compare a computational model of the object that accounts for gravity and drag with an experimental model. So the system in this experiment was the piece of paper, and the surroundings are the earth, or gravity, force, and drag. For the experimental model, I used Tracker, and I tracked the motion of the object frame by frame, and then used those data points to find position and velocity, which I'll talk about in a second. And then for the computational models, I used GlowScript and used code to predict the movement and velocity of the falling object. So here are my initial conditions. The initial position of the object is set at 0, and then the y-coordinate, and then 0, because I set the origin with the x-axis on the floor and the y-axis aligned with where the paper first left the hand that threw it. And you can kind of see this to the right, what I mean here. This is the origin, and this is where the ball left the hand and eventually reached the floor over here. And then to find the initial velocity, 2 points near the beginning of the trajectory were used to calculate the initial velocity of the paper ball. And you can see my calculations here. I calculated the velocity in the y and the x direction. And the x velocity is negative because the ball is going to the left with the way we set up our experiment. So some fundamental principles. First of all, Newton's second law, or the momentum principle. Net force on an object is equal to the change in momentum over change in time, or mass times acceleration. And then forces, we have the drag force, which is opposite to the movement of the object, and this is the formula that we got from the pre-lab. And then force of gravity is negative mass times gravity, where gravity is 9.81 meters per second squared. And then, of course, the velocity update and position update formulas, which are derived from the general kinematic equation. So here's a screenshot of what my lab and tracker looked like. You can see I have the photo here, and then my x position and my y position, and then the data points on the bottom. So this was the procedure. First, I recorded a video of the piece of paper thrown in an arc. I tracked the paper's position in each frame, and by the way, the paper was a ball here, so not a lot of drag. And then using GlowScript, created a computational model for position with regards to gravity. Did the same thing with drag too, and then I used Google Sheets to create a spreadsheet and a graph of both the computational positions and experimental positions over time, and then I compared the models, which I'll go over in a second. So this was my code. I changed the initial time here, just when the ball left the hand is what time I set it to. Delta t to make it a smaller time step, and then the position and velocity vectors that I talked about a second ago, and then the mass of the ball, which we got by weighing the paper. And then here's some more code. This is inside the while loop. I basically gave a drag variable, and I updated that, and then for my model where drag was not accounted for, I just had my b value as 0, and then that f drag force was 0, and then f net was f gravity. So that's how I did that. And then I also updated the bottom part of this code to be the velocity and position update formulas. And then when I graphed everything, this is what I got. So as you can see, my computational models were really close to my experimental model, which is really nice. The red model is the gravity only model, and then the blue is the tracker. So there is a little bit of space between them, especially at the end. So in order to kind of minimize that difference, I included drag, and I kind of used trial and error to make the computational model with the drag force be closer to the final position of the tracker model, and eventually I got that my b value was 0.000268. So a pretty small value, but it did minimize the error a little bit. Speaking of error, some possible errors. Number one, outside influence, like air resistance, which obviously we tried to account for with the drag, but maybe we didn't get all of it. And then not throwing in one plane because there could be a z coordinate that I didn't account for. And then tracking the paper in tracker, it can be kind of hard to exactly get the point of mass down. So a couple what ifs. These are my no drag and drag x velocity. So as you can see with the drag, it's definitely not linear. To reach terminal velocity, you would have to have the drag force equal the force of gravity downwards, and this was not the case in my experiment. But if you wanted to do so in a computational model, you would just have to make sure that that is true. And then if thrown straight up, the object would take longer to reach the ground. As you can see here, I have the general kinematic equation in the y direction, but basically for my experiment, the paper was thrown diagonally, but if it were thrown straight up, there would be more velocity in the y direction, and the delta t would be greater. And that's all. Thank you so much.